Hi everyone, welcome to my channel and thanks for tuning in. The question that I have picked up for today is from Leetcode and it's called binary tree upside down. This question has been mainly used in LinkedIn, so that's good to know. But what is the question? Let's go over the question prompt. Given the root of a binary tree, turn the tree upside down and return the new root. You can turn a binary tree upside down with the following steps. The original left child becomes the new root. The original root becomes the new right child, and the original right child becomes the new left child. So if you have x with z and y as its children, the final result will be y being the root and z and x being its children. The mentioned steps are done level by level. It is guaranteed that every right node has a sibling, a left node with the same parent, and has no children. All right. Here we have some examples. We have example 1, in which we have this tree with 1, 2, 3, and 4, and 5 being its nodes. And the final result is the upside down of this tree with 4 being at the root and 1 being at the bottom most right part of the tree. The other examples are example 2 and 3. So if there's no node, the result would be nothing. And if we only have one node, the result would be the node itself. Let's take a look at the constraints. So the number of trees that will be in range of 0 to 10. And every right node in the tree has a sibling, a left node that shares the same parent. Every right node in the tree has no children. So 3 would not have any children here in this tree, and 5 would not have any children. And if we have a left child, it is guaranteed that we also have a right child, as pointed in here. So as it's common with trees, binary trees specifically, and other questions that we might run into, it's very common to approach these questions recursively. First of all, it's easier to implement, it's easier to understand. Time-wise, the complexity might not be ideal, but it's usually a very good approach. All right, let's draw the tree here. We have 2, we have 3, and we have 4, and we have 5. What's important is to figure out the base case and get some common sequence of statements that we need to do to actually turn the tree upside down and know exactly when to call this same function as we have here, upside down binary tree, recursively. So we can say if root is, which is this node, if root is, for example, null, return root. That's a given. So if you're, for example, here, like we have a null element here, another null element here, we're just going to return the root. So if we are given a null element, or as in the case, for example, 2, we're just going to return the root itself. What is also important is if the root left element is also equal to null, we're looking here, and also its right element is also equal to null, then you want to return root again. In this case, we can't go any further, we can't go down any further, can't traverse anymore, so we're just gonna return the root itself. So this is part of the same conditions. So this would be an OR, and this would be an AND. Although I think as we went over the constraints here, if root, like if any elements left child is already null, its right element will also be null. So we can probably get rid of this, but we're gonna get into the details of that once we're writing the code. The other thing is, at each point, the result of calling upside down binary tree function on this tree, this subtree, is going to be can replace this node here. So we can recursively call this at each point, meaning that getting the result of this, we can get the final root. So if I calculate the result of calling the same function on the left side of this tree, should be root left. I can return that. So in other words, if I calculate the result of this part, which would be 4, 5, and 2, I'm cheating a little bit here. This would also be the root of this one. So if you're giving this original root 1, this 4 would be part of our result. So the result of calling this function on this part of the subtree would actually also act as the root that would need to be returned. But somehow we need to connect these parts. So we need to make sure that we get this at the very end. So to do that, this is where we're actually going to be doing the swap. So we probably have to do it this way. We're going to say that 2's right, which should be 1 itself, and 2's left should be 1's original right. Perfect. So given this knowledge, I think we can get back to the code and start working on our implementation. So let's cover the basic cases. If root is equal to null, return root. Also, if root's left is equal to null and root's right is equal to null, then we should also return root. Now we're going to calculate the left result of our calculation by calling upside down binary tree on the root's left node. So again, a tree node has 3 important elements: a left node, a right node, and its value. These are the 3 main elements or properties or attributes of each tree node instance. So we got this part covered. Now I'm gonna return left result, and here is where we're gonna do the swap on this specific row. So that would look like something like this. So root left would be root right, root left, right would be the root itself, and then root left. So once we do this, let me bring this up. Once we do this, we also need to get rid of these connections. So we need to clear out the roots left and right pointers. So to do that, we need to make these null. All right, let's try to give this a try, give this a chance and run it. We've got 3 correct answers in here. Let's try to submit it. Amazing, this worked perfectly. So we got this part covered. And this is the recursive approach. This is how we can use the recursive approach in this question. We can probably even further simplify this and get rid of this part. I believe this should still work. And yeah, this also worked, and we beat 80% of previous submissions, and the previous one beat actually 100%. Awesome. But let's take a look at this approach. What would be the time complexity of this approach? The time complexity of this approach would be a worst case scenario. We have to interact with all of these elements at least once. So it would be O of n. And in terms of a space complexity, we're just breaking, well, we're not necessarily saving anything, but we're calling this function recursively. So at each point, I believe we're dividing the space in half. And that would make it O of, I think it would still be O of n. Awesome, but we can further improve this. So as I said before, the space complexity would be O of n. Sorry, the time complexity would be O of n. I think the space complexity would still be the same, O of n, because we're using the stack, so we can be able to call this function recursively. Now, let's go back to basics, and we can actually improve the space complexity for this question, and we can, the time complexity will still be O of n, but if we try to follow a recursive approach, we can actually reduce that space complexity to be O of 1. So how can we go about that? It would be sort of a similar approach. We'll still have to do this connections at each step, like changes connections at each step. Well, we need to keep track of a couple things. We need to keep track of the previous node and probably this one at each step. So the top root and the root's right element. We're going to figure that out in the code. Let's get back to the code. What I'm going to say is I'm going to introduce node to be root, because in Kotlin you cannot, all the input parameters of function are by default final, so you cannot use them, which is fine. And I'm gonna introduce another variable called previous, which will be a nullable tree node. And we want to go through this tree as long as the node itself is not null. So as long as the node itself is not null, we're going to traverse the tree. And we need to do a couple things. Imagine we are at this step. So the nodes, we're going to have to set the nodes left and right elements. And let's get that part done. So node right would be the previous node. Nodes left would have to be the previous element's right node. Got that part correct. we need to have a temp value that actually stores node left element, because we're setting it here. So traverse the tree, we're gonna do it this way. We're gonna say node is equal to temp. We gotta save a previous here, so previous would be our current node. And since it's gonna traverse all the way, it's gonna get here and then it's gonna go to the left element of this one, so eventually it's gonna be null. So we wanna return the previous element here. All right, I think this looks good. Let's give this a chance. Okay, we're getting an error on line 20. So this should be null sorted. That's fine. I mean, originally the previous is null, so if you cover it this way, it will also make it to be null in case that it would make its right pointer to be null, even if the node itself is null. Anyways, we got a wrong answer, and it looks to me that we are missing 5 and 3 from the answers, and these are originally the previous right elements. So something wrong with setting up this line. So node left is equal to previous right. Oh, and it makes sense because as we are traversing the tree at each step, we are severing these ties. So the previous right is not actually going to be the original previous node's right element. It's going to be, like in this case, 1, which is incorrect. So because of that, we also need to keep track of the previous node's right element. So I'm just going to add another variable here. And this would be previous right. And previous right is actually going to be the node's right element. Let's give this a try. Okay, still is giving us some issues. Oh, this should be this line should get executed before this one. Yeah. Awesome. This looks great. And let's try submitting this code. Awesome. Great job, everybody. Thanks for tuning in. So this also worked. In terms of space complexity, this algorithm is better because it's O of n, O of 1, a linear time. In terms of time complexity, is the same as the previous one, so it's going to be O of n. Thank you very much for being with me. Stay tuned for upcoming questions. Don't forget to like and subscribe if you enjoy this content. Cheers.